For this video, I'm going to do F1-23. So it's very similar, but the difference here is we have a shear failure. The reason I like this one's a little different because we have to consider, I guess, the twist on this problem is determining what is the area that the shear acts on. Okay, so here we have a bolt head. We're going to idealize this, assume it's cylindrical, and then here is the bolt shank, and it gets pulled through this plate that resists it, so there's a hole here. We're going to assume again that the hole diameter is nominally the same size as the shaft, although there probably is a little clearance. And then there's a downward force of P. Alright? So in this problem, you have to determine P such that we have a pull-out factor safety of 2.5. Okay? So the pull through the plate, alright, these are both the same material, alright? So you have to look at the stresses for pull-out. That there's two ways that it might fail in pull-out. One, the bolt fails, okay? Or two, the supporting plate fails, okay? So there's two ways that it could fail. So we need to check both, all right? Now, let me try to draw it to the side. Maybe I can just indicate it here. So when we talk about the bolt failure, the shear area is going to be a cylindrical interior surface, where these are the sides. So it's kind of, if you look down from the top, right? This cylinder here is the shear area for the bolt head, okay? Now, if we look at in the supporting plate, we're going to make the assumption that the shear area is actually this. All right? Now, why? Well, it's a little tricky. In reality, it's a little more complicated than just pure shear. Shear doesn't happen exactly along a line. But if you think about it, as this pulls down, it's this corner that's going to contact on the plate and cause the shear. So on the bottom side, through the plate, we actually have a bigger shear area. So that's the shear area we're going to consider for the plate. All right? Okay. So it's bigger, but also the plate has is thinner cross section, so that'll bump up the stress. All right. Okay, again, we have the problem given in terms of a yield and then a factor of safety. So this is F1-23. Sorry, you'll have to listen to the phone ring for a couple of seconds. Okay. So we'll do that calculation again. Again, if you're not following this, you can look at the solution for problem 119, and I go through factor safety a little bit. It's a pretty simple concept. All right. So here we're doing shear stresses. So we have a tau max. This is the allowable. Is equal to the tau of the yield over the factor of safety. So in this case, it's 120 megapascals over the factor safety of 2.5. So we have a much bigger factor safety on this, on the bolt, okay? So that gives me 48 megapascals. That's what we have to design to, okay? All right. So first, let's consider the first case. Let's assume that we're going to have a pull-out failure in the bolt head, okay? So remember, that's going to be a shear acting along this cylinder, okay? So in this case, we're going to design it so tau max equals the average shear stress. That is going to be equal to the shear force over the area, okay? Now in this case, the shear force, okay, we can do the free body diagram if you want. Free body diagram, let me try to draw that. It's actually going to look like this. Here we have P, and then here, you know, we've kind of lopped off are the ears of the bolt, okay? And so around this whole cross-sectional area, there is a net shear force V. I always have a tough time drawing this. If you can actually visualize this, this has to be a shear around the whole cylinder. Okay, so in a sense you can put half V on this side and half V on that side, okay? And here you can see obviously that V has to equal P, all right? So V equals P, they're equal, right? Go through the sum of forces if you don't quite see it, okay? All right. Now the area is going to be the cylinder. So this is the circumference, which is pi d. In this case, d is the this diameter, not the 80 millimeter diameter. That's actually the 40 millimeter diameter. It's 40 millimeter times the height of the cylinder, which is this. And that's 75 millimeters. Okay, so that's this shear area. Okay, so we can calculate that out. That is 382 square millimeters. Okay, that's that area, the shear area of the bolt head. Okay. All right. So I don't know what V is, but I know. I know that V is equal to P. So here this has to equal P. I know this, so we can solve for P. P is the max allowable, this 48 megapascal, times the shear area for the bolt head. So that gives me 48 megapascals times the area, which is 382 millimeters squared. Okay, so this is a 10 to the 6th. All right, a millimeter is a 10 to the minus 3rd. So when you square it, you get 10 to the minus 6. So in fact, the millimeters cancel out with the mega, and this gives me a force in newtons, okay? So it's left with newtons, and that is 18,335 newtons, okay? Should be careful about my number of significant digits. I really should say it's more like 18.3 kilonewtons, okay? All right, so for failure in there, the bolt head would fail at 18.3. Now that might not be the max allowable. The failure might happen sooner in the plate, okay? So if the failure in the plate happens at a lower P, then that's going to be our max allowable. So you have to pick whichever one's the lowest. Okay, so now we're going to look at case 2. This is going to be failure, shear pullout failure in the supporting plate. So it's the same deal, except the areas are different.
if we look at the plate now, let me see if I can draw this a little better. Here's one edge of the plate. Here's actually the kind of the part of the plate we're removing from the free body diagram, because this is where the bolt acts on, right? And you know, acting downward on this is going to be P, all right? So that means acting on this, to balance that out, acting on this entire cylindrical shear area is going to be V in the plate. And again, they're equal and opposite, okay? All right. So where are we here? Okay, fine. So it's the same type of analysis. Tmax equals P over the area of the plate. Now the area of the plate in this case, again, is this cylinder. This height here is 30 millimeters, and this shear diameter is the diameter of the bolt head. That's the 80 millimeters. Okay? And so this is pi times the diameter, which is 80 millimeters, times the height of the cylinder, which is 30 millimeters. Okay? So I guess if I were to try to draw it, maybe I could just draw this sort of actually, there's a hole in it, the plate. Oops, sorry. I should draw that. I should draw it like this. So it's this area here, the one that fits into this plug. This is the shear area, just to be clear about it. All right? You can imagine it's taking this. This is what we pulled out, okay? So this has got the V acting on it. P going down, V acting up. All right? All right, so this now becomes 3.1415, 80 times 30 times. This is 40 millimeters squared. So this actually has a bigger cross-sectional area, so it's going to actually fail at a higher stress, all right? And so this will actually have to be the limiting one, but let's go through the calculation. So again, we want to find P, the P max. So P max is going to be the area, the shear area times the maximal allowable stress. So that's the 7540 millimeters squared. The maximum shear is the same as before because it says it's made out of the same material. Often it's not. The plate might be aluminum, the bolt might be steel, and you would have to obviously you could use the same factor of safety, but this number would be dropped because you would have a different yield. All right? All right, so this is, where is it? 382. Oh, wait, I'm sorry, not 382. 48 megapascals. Again, the mega cancels out with the millimeters squared, giving me newtons. And this will come out to be a bigger number. So we multiply this by 48. And this is 362 kilonewtons. Okay, so to pull out the plate, you would need to have a much higher force than you would to pull out the bolt. So the bolt head will fail sooner. So this is the max allowable P. Okay, this is your answer. Okay, so the plate doesn't fail into this, but you always pick the lower of the two, right? The worst case scenario. Okay. All right. So just be careful. If you don't quite understand the shear area, think about it a little bit. But if you still understand it, why don't you try to ask me a question in class or pull me aside later? Okay.